Hey, in this video we're going to have a look at how to remove duplicate elements in a list. So we're basically going to turn it into a set where there's no duplicates and we're not going to be concerned about the order. So the general strategy here is we're going to use tail recursion and an accumulator again, and this is how we want the query to be written to the console. So provide a list and we'll put the result back into this set variable here. So we want to just isolate the head and tail again, so we can do this by using the head and tail notation, but I'll cover that when we do the coding. But the tail will therefore be 1 and A, the list, and then we want to set the accumulator to initially be just an empty list, and this is going to help with identifying if there's duplicates or not. So next we just need to ask ourselves a couple of questions, and for this predicate there's going to be a couple of other predicates involved so we can cover all the conditions. So we just need to ask ourselves a couple of questions, and the first one basically is that if you pay attention to the relationship between the head and the accumulator, so if we just say to ourselves, if the head is a member of the accumulator, don't do anything and go ahead and process the tail, because if the head's already in the accumulator, we don't want to add the head to the accumulator again, because that's going to defeat the purpose of removing duplicates. Otherwise, if head isn't a member the accumulator, then we want to append the head to the accumulator, then go ahead and process the tail again. So those are the two conditions basically. If A is a member of the accumulator, we don't want to do any appending, we're just going to go ahead and continue to process the tail so we make progress towards the base case. And then if H isn't a member of the accumulator, then we need to add it to the accumulator so we can build up the final result. So keeping this in mind, the very first thing that happens is that the accumulator on the first step will be set to A, because A isn't contained in this list of the accumulator, and that's what the member built-in predicate does. It just checks for if an element is contained within another list. So then we just go ahead and call ourselves again, but this time we pass in the tail. So the tail gets passed in to here, and then we go ahead and we isolate the head and tail again. So the head will be 1, the tail will be just A, and the previous accumulator is going to be A. But then we just need to ask ourselves these two questions again. If head, which is 1, is a member of the accumulator, then we don't need to do anything. If 1 isn't a member of the accumulator, then we need to append 1 to A to make a new accumulator value. So we'll go ahead and do this. So the new accumulator is going to be 1 and A, and then we call ourselves again using the tail. So this tail gets passed in to here, just like before. Then we extract the head and tail again. The tail is empty because there's nothing after A. And then we just need to ask ourselves these two questions again. So this time head, which is A, is a member of this list, So therefore we don't do anything, we don't append any value to this, we just keep this accumulator as it is. So that means the accumulator stays the same, but instead we need to keep making progress towards the base case. So we recursively call ourselves again, passing in the tail, which is the empty list. And because we're at the empty list, this is a good candidate for a base case. So we need to consider what we should do now. Because we're using tail recursion, we're right down the bottom now, and the result is built. So we need a way to, this accumulator will have another third variable set up somewhere. So our base case will end up being something like this, where, like the other videos, it just simply transfers the accumulator into the final result variable. So it will be like accumulator, and the accumulator will end up being binded to the value of the list 1a, and that will get binded to the third argument position, which in turn will set the final result to 1a, which will bubble up to the top, which is what the final answer the query caller will see. So that's the general process of reducing this and getting rid of the duplicates. So now we'll jump into the code and have a look at how to code it up. So the process is pretty much following the same sort of trend as before. In the last couple of videos, we don't want the query caller to have to write the accumulator into their query. So we'll abstract this away and create an interface, so to speak, for it. So we'll just create a predicate that exposes the list and the set, and then we'll call a helper predicate to do the actual recursion work for us. So we'll just pass through everything, but instead we'll just give the second argument position an accumulator, and this is going to hide the implementation details away. And then what we need to do is we'll just go through and do these rules. So in Prolog, unlike other programming languages, you can't say we define this other predicate here inside the rule head. We've got the rule head here. Inside the rule body, you can't write statement 1 here, and you can't write if this happens here then else do this. You have to write 2 separate predicates to do both the different rules. So we'll define the first predicate first. So what we want to do is we want to accept a list, and the second argument position we want to be the accumulator. The third argument we just want to carry on with accepting the third argument set, which doesn't have a value yet, but we'll set that when we do the base case. And because we want to extract the head and tail out each time, we can just do a shortcut here with using the head and tail with the bar notation, which will isolate the head and tail from each other. So then it's just a matter of going through what these rules say. If H is a member of the accumulator, so the way we write this is member H accumulator. Because this is a conjunction, this semicolon means conjunction, which is a logical AND statement. So if this is true, and this next thing will get tested for true or false. So if H is a member of the accumulator, don't do anything and go ahead and process the tail. So that just means then we'll just recursively call ourselves with the tail this time, and we're not doing anything. So that implies just pass through the accumulator as it was before, and that's pretty much the first rule done. It doesn't do anything really, because it doesn't make sense to append a duplicated value onto the accumulator. So now we go ahead and do this second rule. So we have to basically just write this out again and change it a little bit. So if H isn't a member of the accumulator, so in this top predicate here, this rule says if H is a member, but if this fails, then that implies that they're not a member, so you don't have to do anything here, because this predicate here already did that for us. It's because this predicate is defined after this one, which is how we can infer that they're not a member, which means we need to append the head to the accumulator. So this is where we append the head to the accumulator to get the new accumulator result. So you can write this two different ways. New accumulator equals the head bar accumulator, and like I said previously, what happens here is that initially the head is going to look like this, head bar accumulator, which really looks like this, head bar an empty list, but a bar followed by a list means that the bar removes the list and unpacks the elements inside it. There's no elements inside this list, so what you'll get is whatever the value of head is, which is A, and the bar removes the list, so it just gives you A. So that's what this is saying here, which means the new accumulator will be set to A for the first time around, and that means that we recursively call ourselves by using the tail, and the new accumulator, which is going to be A, which is passed through here. But you don't have to write this in two separate stages, you can directly just dump this directly in here, which makes it a little bit neater. And that's all you have to do for the second rule, because we've done the appending and we've passed through the tail to go to the next recursive call. And that looks good to me. We continue basically going through this, and then we need to do the base case. So the base case, we said that we'll eventually reduce the tail to an empty list. So if we're on the last stage here, tail here will be an empty list, and then prolog, when prolog recursively calls itself, prolog will go to the top of the knowledge base and scan down for a factor rule that's going to match with an empty list. So we need to define something, another predicate or a rule to match on the first argument being an empty list. So we need to make sure the first argument's an empty list, so that when this last recursive call happens, we can stop what we're doing and calculate the final result. So we said that we want, because we're doing tail recursion, the accumulator at the end of recursion will store the final value. So we want to store the accumulator into a variable, because a variable in prolog in the unification process can bind to any value. So we need, in the second argument position, we need to have some variable. It can be called anything you want, doesn't matter, but it's an accumulator, so we might as well name it that. And we want the accumulator value to be binded to the third argument position, which is going to be the set variable that the query caller provided, which they'll eventually see the value in. And that's pretty much done. So that's what the whole thing looks like. It's more just trying to piece together how it works inside your head, because the main idea is that this final stage is what makes it all work. It binds the final value of the accumulator to the third argument position, and if you followed along my videos, these third argument positions all have a relationship set up with each other. So once this value here is binded to the third argument position, because there's an unbinded variable in the third argument position which each share the same memory address location, the result list of 1A will be bubbled up to the caller of the initial query, which is why they'll see set equals to the list 1A in the console. So we'll go test this out. I'll save that and reload the file. All good. So now we'll just test out some values. What did I have? A1A. A set. So yeah, you can see that duplicate A is removed. You can just be crazy here to find some other values. A 1 1 1 A, and yeah, now there's 3 unique elements. All the other duplicates are gone. So yeah, I hope that video sort of builds upon the last two, where we introduced a member predicate and sort of identifier when something is a member of a list and when something isn't, and how to create sort of conditions by using the same predicate name to create another rule, which in turn creates the two different conditions. And yeah, just remember that during the recursion process, if we do a trace here, this variable G1342 is going to be this third argument position here, which is shared across every recursive call, which is why when you get to the last base case position, whatever value is binded to this variable is what's going to be seen in the third argument position, in the second argument position by the query caller, which is how that they see the final value printed to the console. But yeah, thanks for watching and hope to catch you next time.